Dear students, now we prove the most important theorem, that is called Pullback Theorem. So what is the statement of Pullback Theorem? Let xd and y row be two metric spaces and f x to y is a function. Then f is continuous on x if and only if f inverse g is open in x for every open set g in y. That means x, y are two metric spaces, f is a function from x to y. If f is continuous on x, if and only if f inverse g is open in x for every open set g in y. That means under the continuous function you pull back from open set to open set. Similarly, under the continuous function you pull back from closed set to closed set. This is known as the pullback theorem. If g is open in y and f is continuous, then f inverse g is open in x. That means we pull back from open to open. I am turning the pull back. Pull means pelli ba turning pullback theorem. Open to open. Similarly, close to close under the continuous functions. Let f x to y is continuous. It is given. We have to show that f inverse g is open in x for every open set g in y. Suppose g is equal to, and we have to show that g is open in y. We have to show that f inverse g is open in x. Suppose f inverse g is equal to x. Body ki x is saman hai. What happens? Case 1, let f inverse g is open in x for every open set g in y. Case 1, let f inverse g is equal to x, which implies f inverse g is open in x, because we know that every whole space is open and null set phi is also open. Similarly, case 2, let f inverse g equal to null set phi, which implies f inverse g is open in x, because the null set phi is both open as well as both. That means it is open. Then under the continuous map, we pull back from open set to open set. Case 3, suppose f inverse g not equal to x and f inverse g is not equal to phi, then we have to prove f inverse g is open in x. That is the case 3. When f inverse, we have to show that f inverse g is open in x. It is given that g is open in y. Suppose f inverse g is equal to the whole space. We know that the whole space x is open. So case 1 is open. Suppose f inverse g squeezes, that is equal to null set phi. Then f inverse g is also open, because we know that the null set phi and whole space x are both opens. Let us consider the case when f inverse g is not equal to phi and also not equal to x. We have to show f inverse g is open. In order to prove f inverse g is open, it is sufficient to show that every element of f inverse g is an interior point. Let's take a point. Let x belongs to f inverse g, which implies fx belongs to g. Since g is open and fx belongs to g, then each element of g must be an interior point. Then fx is an interior point of g. Since fx is an interior point of g, then there must exist a open sphere of radius epsilon of fx such that this is a subset of g for some epsilon greater than 0, equation number 1. Since fx to y is continuous, then there must exist delta greater than 0 such that f of s delta x is a subset of s epsilon fx. This is equation number 2. From equation 1 and 2 we have f of s delta x is a subset of g, which implies s delta x subset of f inverse g. There exists delta greater than 0, the open sphere s delta x such that s delta x is a subset of f inverse g, which implies x is an interior point of f inverse g. Since x belongs to f inverse g is arbitrary, then each element of F inverse G is an interior point. By definition, open sets F inverse G is open in X. That means under the continuous map, we pull back from open set to open sets.